Hi, it's me, Paula, the math tutor. In this video, we're going to discuss binomial situations. We are going to introduce the concept of binomial distribution. So for that, we are going to count binary outcomes. We are going to remember Pascal's triangle, or introduce it if you've never seen it. Then we are going to incorporate probabilities to those binomial outcomes. And finally, we are going to define what a binomial situation is. So, let's begin. Imagine you're playing a game, and there are only two possibilities, winning or losing. We're going to imagine we play this game several times, and we are going to represent in this table the number of games we play, the possible outcomes with 0 win, 1 win, 2 win, depending on how many times we play. And then we're going to analyze the pattern of those outcomes, and we're going to realize something interesting happens. So let's say you play this game once, and remember, you can either win or lose. So you could either win 0 times, so you lose, or you could win 1 time. Now let's add another trial. Let's say you play 2 times. You could either win 0 times, so you lose the first one and you lose the second one. We're going to represent that with lose-lose. Then you could win 1 time. You could either lose the first trial and win the second one, or you could win the first one and lose the second one. So you have win-lose or lose-win. There are 2 possibilities for this. And you could win both times. So win and win. The pattern we get then is 1 outcome for winning 0 times, 2 outcomes for winning 1 time, and 1 possible outcome for winning both times. Now let's say we play this game 3 times. In this case, we could win 0 times. So we lose, and we lose again. Then it could be that we win 1 time. And here we have 3 possibilities. We could either lose the first 2 and then win the third, lose, then win, then lose, or win the first time and then lose the second one and the third. And we could also win 2 of the 3 times. In this case, we also have 3 possibilities. We could win, win, lose, win, or lose, win, win. And we can also win the 3 times, and that is 1 possibility, 1 only possible outcome, which is win, win, win. If we count the number of possible outcomes, we have 1 for losing 3 times, 3 for winning 1 time, 3 for winning 2 times, and 1 for winning 3 times. Now let's say we play this game 4 times. For 0 wins, we have only 1 possible outcome. Losing. We could also win only 1 time. And in this case, we have 4 possible outcomes, because we could win and then lose all of them, or win in the second trial, or win on the third one, or win on the fourth one. Then we could win 2 of the 4 times. And in that case, we have 6 possibilities. All of this. For winning 3 of the 4 times, we have 4 possibilities, and for winning the 4 times, there's only 1 possible outcome. So the pattern we get of the possible outcomes is 1 for losing all of them, 4 for winning just 1, 6 for winning 2, 4 for winning 3, and 1 for winning all 4. If you see the pattern that we're getting in this table, you may recognize it if you remember Pascal's triangle. This is a numerical triangle that starts in the top with a 1, and then each row is the same. Each row starts and ends with a 1, and all of the numbers in the middle are the result of adding the 2 numbers above it. And each number in this triangle could be seen as a peg, or a decision, a fork in the road. This number tells you how many paths you could have taken from the top to get to that one. And this triangle is very interesting for many things, but for counting binary outcomes is extremely useful, because each of these numbers in each of these rows it's going to give me the combinations I can make, all the possible outcomes I can get by combining a certain amount of numbers in a certain amount of ways. So for example, let's say I want to know how many ways can I win in this game exactly 5 times if I play 7 times. Then first I need to go to row 7, and there I need to start from the left and count to 5. Where I land is my number, and in this case I land in 21, which means that there are 21 ways of winning 5 times if you play 7 of them. And Pascal triangle, the good thing about it is that it's very simple to get. You start with a 1 on top, and then you start with that pattern of starting with a 1, then adding the 2 numbers on top, and then when you only have 1 number left on top, you put a 1. So the last number is going to always be a 1. The difficult thing about Pascal triangle though is it's fairly easy to make when you have a low amount of rows. But let's say I want, I don't know, 20 rows or 50 rows or 100. I'm not going to write all of that. But because these numbers represent the number of ways I can combine a number of items in a certain amount of way, these are actually combinations. If you remember, combinations can be calculated using factorials. This is the formula for combinations. Or also you can do it in your calculator. But each of these numbers is going to be the combinations of a certain number n, which is represented in the number of rows in the triangle, and a certain amount of numbers I choose. So for example, if I want to find the number of ways I can win 5 times, if I play 7, I'm going to be calculating combinations of 7 choose 5. Now let's incorporate probabilities to this. Again, let's go back to this game where we are playing and we can either win or lose. Let's say the probability of winning is 1 over 6. If we play this game 1 time, what will be the probability of either winning 0 times or 1 time? Well, if the probability of winning is 1/6, the probability of losing is everything else. So it will be 1 minus 1/6 or 5 over 6. Meaning that the probability of winning 0 times is going to be 5 over 6, which I'm going to write as 5 over 6 to the power of 1. You'll see later why this exponent is interesting. For now, let's just leave it there. And the probability of winning is 1 over 6. So I'm going to write it as 1 over 6 to the first power. Now let's play this game 2 times. What is the probability of winning? 0 times, 1 time, or 2 times? Because each trial is independent, each game we're assuming it's independent of what happened in the previous one, the probability of winning 0 times is going to be the probability of winning 0 times the first time times the probability of winning 0 times on the second one. So it's 5 over 6 times 5 over 6, which I can write as 5 over 6 to the power of 2. The probability of winning 1 time, I could either lose and then win, which would be 5 over 6 times 1 over 6, or I could win and then lose, so it's 1 over 6 times 5 over 6. If I add these two, I have 2 times 1 over 6 to the power of 1 times 5 over 6 to the power of 1. And the probability of winning both times would be the probability of winning the first time times the probability of winning the second time. So it's 1 over 6 times 1 over 6 or 1 over 6 squared. Let's say we play 3 times. Then the probability of winning 0 times would be losing the first one, losing the second one, and then losing the third one. So it's 5 over 6 to the power of 3, because I'm multiplying it 3 times itself. Then, for the probability of winning 1 time, I have 3 possibilities of winning 1 time. We saw that when we were working with the table and then with the Pascal triangle. So the probability of this would be 3 times 1 over 6 to the power of 1, because I'm winning 1 time, times 5 over 6 to the power of 2, because I'm losing 2 times. Now, for the probability of winning 2 times, I will have, again, I have 3 possibilities of winning 2 times and losing 1. And each time I will be multiplying 1 over 6 times 1 over 6 times 5 over 6. So what I get is 3 times 1 over 6 to the power of 2 times 5 over 6. And then the probability of winning the 3 times, it will be 1 over 6 to the 3rd power, because it's 1 over 6 times 1 over 6 times 1 over 6. Do you see this pattern? We are always, the first and the last probabilities are always 1 times 1. And then the middle one, we are getting the numbers of the Pascal triangle. So what's happening here for the probabilities of this situation where you can either win or lose is we're multiplying the coefficients we're getting from the Pascal triangle, so the combinations of each of the things happening, the combinations of how I can choose each of the things happening, times the probability of winning to the power of how many times I'm calculating it for, how many wins I have in that case, times the probability of losing the other times. So it will be the total number of times I play minus the times I won. That will be the exponent for the probability of losing. And this pattern is going to repeat whenever you're working with binomial situations. So let's define. A binomial situation is going to be any random process where there are only 2 possible outcomes. We are going to call those outcomes success or failure. Again, you win or you lose. Something happened or something doesn't happen. That's the only way it can work for it to be binomial. Then we have a set number of trials. We try this n times. And we have the probability of success, which let's call it P. And then the probability of failure, let's call it Q, but that is going to be 1 minus P, because as I can either fail or succeed, the probability of failure is 100% minus the probability of success. Those two are going to be constant, so for each time I try this, the probabilities stay the same. So if this happens, the likelihood of a certain number of successes, x, can be expressed as this, with this formula, this probability. It's combinations of n choose x times p to the x power times q to the n minus x power. What these numbers mean is combinations of n choose x is the number of ways to arrange the successes and failures. This is the number of ways I can get this winning a certain amount of times or succeeding a certain amount of times in the total n. Then I have the probability of each success to the power of the number of successes I'm expecting. And then I multiply times the probability of each failure to the power of the number of failures I have in that case. Because the number of failures is going to be the number of times I don't succeed, it's n minus the successes. And this formula is going to allow me to calculate the probability of binomial situations. In the next video, we are going to discuss what it means for a situation to be binomial, how you can recognize a variable having what we are going to call binomial distribution, and then we're going to see a bunch of examples of how to do this, both by hand and in the calculator, because as you can see, the formula takes a little bit of work, and you will usually be expected to do this with technology. So I hope to see you there. Bye bye!
Okay.